Hi, it's time for another math easy solution. Today we're going to discuss further into linear differential equations, and now I'm going to look at the integrating factor in more detail, and this will make more sense as I get through this, why I'm doing this. Basically, recall from my earlier video called linear differential equations, where I went over the general solution of the first order linear differential equation, this one right here, dy over dx plus p of x times y equals q of x, where the p and q are just functions of x, and then basically the solution is given by the formula, and I derived this y of x equals to 1 divided by I of x, where I is the integrating factor, and then times it by integral of I times q dx plus c. Yeah, so this was what I went over in that video, but now what I want to do is recall the derivation of the integrating factor I of x, or this one right here, was actually derived more generally in that video as I of x is equal to a e to the integral px dx, like that, where basically a is just a constant. So a equals to constant. Yeah, and we could even go there, so let's just go to linear differential equations here, and let's go, yeah, so basically in the derivation, this is that video, this is from that video, you can go and see it, I'll put the link below, but when I was looking for the I of x, the derivation, it got to here, I of x equals to a e to the integral p dx, and where a was plus or minus e to the power of c. But then in that video I went over and I stated that we just needed one particular integrating factor, not the most general, so we chose a equals to 1. So let's go back here. Yeah, and here I wrote that down, but I stated before that we only need one particular non-zero solution, so we chose, or we choose, so put a, yeah, so we chose a equals to 1, and in this video I'm going to look at when we don't set the constant to any value, just look at it generally. Also in the previous examples I showed that when integrating I of x, a constant of integration arises, but even then I chose it to be equal to 0 because we only need one particular non-zero solution. If you have 0, it just doesn't make any sense, and it can't even be 0 because the constant is plus or minus e to the c. Anyways, regardless, it can't be 0 because if I of x is 0, it just you just have a trivial answer. Yeah, so here again in my previous examples, for my last video on example 2, so recall example 2, where in that video we had p of x is equal to 1 over x in that case, and also where x was greater than 0. So when we solved the integrating factor I of x, so I of x, we chose again a is equal to 1, so we had I of x is e to the integral p of x dx, which equals to e to the integral 1 over x dx, and then when you integrate this becomes e to the ln absolute value of x, its integral of 1 over x, plus a constant of integration c, but then we just chose this to be equal to e. This one is going to be x is greater than 0, so ln x, and then c is 0, and then these just cancel, and this is x. And again, the reason is because here we chose c is equal to 0, and also we know that put a bracket here, x is greater than 0. So that's why the absolute value sign goes away. So the reason we chose c is 0, again, because we wanted one particular solution. Yeah, but now in this video what I'm going to do is basically verify that we can actually go ahead and do this, or in other words that the constant value doesn't matter what it is. So now to verify my previous claim that we only need one particular solution of I of x, let's take a look at what happens if we don't choose any values for the constants that arise. So basically let's start off with the differential equation, linear differential equation. So we have y prime plus p of x times y equals to q of x, like that. Just write this a bit neater. Yeah, so we have something like this, and then we're the integrating factor I of x, so when we don't let the constants, we don't choose it, so we have a e to the integral px dx. Yeah, let's write this a bit bigger, like that. So, yes, so now that we've accounted for this constant, let's account for the integral constant there. And what we'll do is, to do that, because we don't have a value for p of x, so we'll just let the derivative of capital F prime of x equals to, well, first of all, this one, the same thing as writing d f of x over dx, the derivative of that, and then this equals to, so what we're going to do is let this equal to p of x, or the integrand. So we're going to let the derivative equal to the inside of that, and the reason we're doing that is because, well, now we have a separable equation, move this over there to the dx. So what we have now is a df of x equals to px dx, and now we can just take the integral of both sides. And then when we do that, we'll let this one just remain as is, so, but the left side, the integral of the df of x, this is going to be just, well, capital F of x plus the constant of integration, and the right side will keep it as is. So, this is going to be integral of p of x dx. So in other words, this part right here now equals to this whole thing, this whole integral becomes just f of x plus c. So we've accounted for our constant. Yeah, so we'll write that here. So thus our integrating factor is now I of x is equal to a e, and now f of x plus c. Yeah, so now that we have this, but we can go further here. We can simplify this by using the logarithmic, the power rules. Whenever you have an addition in the power, we can multiply it if it's the same base. So in other words, this equals to a, and then we're going to bring this down. So e to the power of c times it by e to the power of f of x. Yeah, and now what we could do is, well, set this equal to d. So I'm just going to combine these together because a is a constant, e to the power of c is also a constant. So we have d times e to the f of x, where we have d is equal to ae to the power of c. Yeah, and then this just equals to a constant. So whenever you have when you take a constant, make it a power of a number, and then multiply by another constant, it's all just a constant. Yeah, so now that we have all this there, now we could plug this into our giant formula. Let me just go scroll up. So now the solution to this differential equation is this. So let's just write that down for our new value of I of x, which is d times e to the power of f of x. So we have y of x is equal to 1 over, I'll just write this down first for completeness. So 1 over the integral of I of x times it by, 1 over I of x times the integral of I of x, and now q of x dx, and then we have to add the constant c. Yeah, constant c, and this c is not the same as this one. This one is just for constant of integration into here. So this one is not the same. It's just a random constant. We'll just to let you know. So now that we have it over there, what we have now when we plug in our value, so 1 over d e to the f of x, like that, and then the integral. Now we have again d e to the f of x inside, and then q of x dx plus a constant c. So now what we could do is, this is just a constant d, so we can take that out, and then that cancels with this, and then we're going to also divide this inside the c, so we'll have c over d. So what we get now is this cancels, so we get now 1 over e to the f of x, and then we have the integral, and then the d's cancel, so e to the power of x times it by q of x dx plus c over d. Yeah, so now that we have that, but let's just combine these into the number e. So I'll erase this, and I'll write this e, so just another constant, where e is equal to c over d, and this just equals to a constant like that. Yeah, so as you can see, this equation is pretty much the exact same as above. So if we change that f of x, yeah, if we change that to that integral p of x, so let's just write that down. So basically where, if we recall, we had set that if we just go up here, yeah, here's that the integral right here, so I of x is equal to that a times e to the integral p of x dx, so where I of x is equal to the ae integral now px dx, like that. And now this part right here equals 2, well, because the integral p of x dx is just f of x plus c. So this means we have ae and then f of x plus c. Yeah, instead of saying where, I'll just write recall. So recall, just because we have a where there, just seems a bit awkward. So, yeah, so this is our I of x, and now if you look at this equation, this is the exact same thing as this one here. I of x is now becoming, it's the same exact look. Instead of c, we have e, but they're still constant. So there's no difference between this and this, because you still have to solve for the constant, and it basically, this c over d just combines a constant into another constant. So nothing changes. This overall value is going to be the exact same when you solve for it. But notice this I of x, it goes to here, e to the power of f of x. There's the e to the power of f of x as well, and then the d just cancels, and we could make it look like that by setting this equal to. So this equals to, well, e to the f of x, where, and this is just choosing a equals to 1 and c equals to 0. In other words, it doesn't matter what constant you use. You could use 100, and you're just going to divide by this constant by 100, because these ones cancel, so you're going to divide by it. So it doesn't matter what it is. So 1, so we just make it equal to 1, so this equals to that. So the simplest one is just letting it equal to 1 and 0, so that we can get rid of these constants out of the way. So we have a non-zero integrating factor. Yes, so thus wrote it down here, it does not matter what the constants of integrations are in the derivation process, because the final constant of integration in the solution takes this into account. Whatever the constant you choose, you're eventually going to divide by this constant, so it doesn't matter, and it's just still a constant. Thus, all is needed is one particular solution of I of x, and then usually just pick the simplest one. So C0, a is equal to 1, we get this e to the power of f of x over here. So, yeah, that's all for today. Hopefully you learned from this. A pretty interesting video on the integrating factor, and why we could just ignore, just set the constants to be 0 or 1, etc. Just because we just need one solution of this particular, one particular solution of this integrating factor. From there we can plug this into here, or multiply both sides of this and solve it as explained in my earlier video and in the examples. Anyway, that's all for today. If you learned, like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.